All right, let's talk about a piece of engineering that most of us never see, but that quietly protects millions of lives every single day. Hidden away in the guts of our buildings, there's a machine that just sits there, waiting. But when things go wrong, its performance is literally a matter of life and death. We're talking about fire pumps. You know, when a fire breaks out, this is the machine that absolutely roars to life. It has one job and one job only: to supply a massive amount of high-pressure water to a building's sprinkler systems and the hoses for the firefighters. It is the last and most powerful line of defense. A guardian angel, really, just cast in iron and steel. Honestly, the best way to think about a fire pump is as the active beating heart of the whole system. The pipes, well, they're the arteries and veins. The sprinklers are like the capillaries. But it's the pump that provides that vital pressure, that heartbeat, that pushes life-saving water to every floor, every corner, right when it's needed most. Without it, the whole system is just a bunch of useless pipes. Now, you can imagine, for a machine this critical, good enough just doesn't cut it. It has to be as close to fail-safe as humanly possible. And that's where the National Fire Protection Association, or the NFPA, comes in. They literally write the rule book. We're talking NFPA 20 for how they're installed and NFPA 25 for how they're maintained, to make sure every single fire pump is built and cared for to the absolute highest standard of reliability. So, how does this thing actually work? And maybe more importantly, how do we guarantee it never fails? Well, here's what we're going to cover. We'll start with its critical role, then we're going to get our hands dirty with the engineering, looking at the pump's anatomy and some incredible tech in its seals and bearings. After that, we'll learn how to read its performance curves. It's like its DNA. And finally, we'll see how the NFPA's strict rules for inspection, testing, and maintenance keep this machine ready to go at a moment's notice. So let's start with the basics. Why do we even need these things? I mean, water comes out of the city pipes, right? Well, sure, that pressure might be fine for your house or the first few floors of a building, but it is completely, totally inadequate for a high-rise. The fire pump's job is to take that city pressure and boost it, sometimes exponentially, to make sure that even on the very top floor, there's more than enough force to knock down a fire. And here's a really critical point, taken right from the NFPA standard itself. The ultimate responsibility for this life-saving machine? It doesn't just fall on some mechanic or an inspector. Nope. It falls squarely on the shoulders of the building owner. It is a legal, and I would say ethical, mandate to make sure that system is always ready to go. All right, let's pop the hood and get into the engineering. How does this machine actually work its magic? Well, at its core, the most common type of fire pump is a centrifugal pump, which is just a beautiful marvel of fluid dynamics that turns rotational speed into immense pressure. So what you're seeing here is a cutaway, and what's so cool about it is how elegantly simple the concept really is. You've got the main players right there: the impeller, which is the part that spins the water, and the casing that contains it all. But don't let that simplicity fool you. Inside, every single one of these components is precisely engineered to work together flawlessly under the most extreme stress imaginable. Okay, let's break it down. So the motor spins the shaft. The shaft spins the impeller, which acts kind of like a high-speed slingshot, just flinging water outwards at incredible velocity. That water gets thrown into this snail shell-shaped casing, which is called a volute, and its clever design forces this super fast-moving water to slow down and expand. That conversion from speed to force is the fundamental magic of a centrifugal pump. And of course, you've got seals and bearings making sure the whole thing holds together and spins as smoothly as possible. Now let's zoom in on two of those components that are just absolutely critical for reliability: the seals and the bearings. I mean it. If either one of these fails, the pump fails. Period. They are the true unsung heroes of this machine's incredible durability. Think about this for a second. Sealing a shaft that's spinning thousands of times a minute while holding back hundreds of pounds per square inch of water pressure, that is a massive engineering challenge. What you're looking at here are two different designs for mechanical seals. And the choice between using one big, robust spring or a bunch of smaller springs, that decision depends entirely on the specific demands of that pump: its speed, its pressure, and its size. And next up, we have the bearings. The traditional workhorse is something called a journal bearing, where the shaft basically rides on this micro-thin layer of oil. It's proven technology, it's effective, but the real cutting edge is magnetic bearing technology, which uses these powerful electromagnets to actually levitate the shaft so it never physically touches anything. How cool is that? And this diagram just illustrates that principle perfectly. You have these coils of wire creating magnetic fields that are constantly adjusting thousands of times a second to keep that rotor perfectly centered in its housing. So what's the result? Well, you get zero friction, zero wear, and just incredible efficiency. It is a huge leap forward for pump reliability. So, we've looked at the individual parts. But how do engineers know for sure that a specific pump can actually do the job it's designed for? They don't guess. They rely on these incredibly detailed performance curves. You can think of these charts as the pump's unique operational DNA. They spell out exactly what it's capable of and where its limits are. Okay, I know this chart might look a little intimidating at first, but it tells a really important story. It shows how a pump's efficiency changes based on its flow rate, that's in gallons per minute, or GPM, and something called its specific speed. Each of those curved lines represents a different pump, and you can see for every single one, there's a sweet spot where it performs at its absolute best. So the whole game is about finding that sweet spot, which is known in the industry as the best efficiency point, or BEP. And operating a pump at its BEP isn't just about saving electricity. This is the point where the pump runs the smoothest, with the least vibration and the least stress on all its components. And a pump that isn't stressed is a pump that's going to last longer and, most importantly, is way less likely to fail in an emergency. It's about maximizing both efficiency and long-term reliability. And get this, the peak efficiency can be absolutely incredible. A well-designed centrifugal pump operating right at its BEP can be over 90% efficient. That means 90% of the energy coming from the motor is converted directly into life-saving water pressure, not just wasted as noise or heat. Which, brings us full circle. All of this incredible engineering, this relentless pursuit of peak performance and reliability, it's all completely meaningless if the pump doesn't work when it's called upon. And this is where the NFPA's mandate for ongoing readiness is so important. The entire program is captured in one simple acronym, ITM. That stands for Inspection, Testing, and Maintenance, and it's a rigorous, non-negotiable schedule of procedures designed to guarantee that a fire protection system is in a constant state of readiness. Because this is what happens without ITM. You're looking at the inside of a valve from a fire protection system. That severe corrosion and buildup can literally choke off the water flow, rendering the entire system useless. It's a silent failure, just waiting to happen. So the ITM cycle is the solution to that problem. It's a continuous loop. First, you have regular inspections to visually spot potential problems, things like leaks or damage. Second, you have periodic testing, where you actually operate the pump and measure its performance against its design specs. And third, maintenance, where you fix any problems you found during the inspection or the test. Simple as that. And the absolute cornerstone of this whole process is the annual flow test. As the NFPA handbook itself says, this is the moment of truth. It's not enough to just flip the switch and see if the pump turns on. You have to test it under realistic flow conditions to confirm its performance hasn't degraded over the last year. And the criteria here are incredibly strict. A pump's performance today is measured against its original, factory-certified test curve from the day it was built. If that annual test shows its pressure and flow have dropped below 95% of that original performance, it is no longer considered acceptable. An investigation is required, immediately, to find and fix the cause. There's no wiggle room. The fire pump is just a perfect example of a system where failure is simply not an option. This combination of precision engineering and mandated rigorous maintenance is really a model for reliability. And it makes you wonder, where else in our daily lives, from the power grids we rely on to our clean water supplies, does this hidden world of tireless machinery and uncompromising standards keep us safe? It's something to think about.